So this video is going to cover the basics of parsing and context-free grammars. Just a reminder that after we've gone through the scanning phase of the compilation process, the next step is to do parsing. Basically, what parsing is going to do is take this collection of tokens and arrange them in a way that is meaningful and recognize that the actual source code follows the rules of the language. The rules of the language are described by the grammar that defines the language. A grammar is something that has been used by linguists to describe natural languages, such as English, but computer scientists took those basic ideas and applied them to describing programming languages as well. Now, the quality of the grammar is absolutely going to determine the quality of the compiler. Basically, the process of creating a compiler is pretty well defined, and there are lots of good existing tools that will help you generate a compiler as long as you have a good grammar. However, if your grammar is flawed, then your compiler is going to be flawed. So you need to make sure that you spend a lot of time ensuring that the grammar is good. The whole purpose of parsing is basically to generate a parse tree. That parse tree is going to not only contain the actual tokens of the source code, but also put them in context. And from that parse tree, you can then generate the code that you actually need. If you can't create a parse tree based on the grammar that you have defined, then the sequence doesn't exist in the language. If you can create a parse tree, then the sequence does exist in the language, and again, you're providing context for those tokens. It's not just a jumble of tokens, random tokens, it's actually a program with meaning at that point. So a context-free grammar requires some tools for defining it. We have the idea of tokens or terminals. These are the tokens that are generated by the scanner, and this is actual characters that appear in the source code. We also talk about non-terminals or variables. These are abstract components that are describing different parts of the source. So something like a selection component of our source code or some kind of repetitious component of our source code. These are the kinds of things that would be described by non-terminals. We use angle brackets as notation to indicate that something is a non-terminal versus terminal values that could appear in the code or source code. And there's something designated as a start symbol. So that's where you would start all of your evaluation of the source. We have also production rules, which are basically our non-terminals are going to be expanded into according to some rule, and that rule may involve other non-terminals, or it may involve terminals, or a combination of those things. It's very possible that you have more than one rule for a single non-terminal. And it's also very possible that there's some kind of recursion involved in these rules as well. So here's a sample of context-free grammar where we're describing some simple sentences. We have this idea of a non-terminal. In particular, this is our start symbol, which is going to identify where we start in our evaluation of our source. We're identifying what it means to be a sentence. And then we have other non-terminals as well, like noun phrase here. We also have the idea of terminal values such as the or dog. These would be tokens that would exist in our language. And we have our production rules. So something like our verb phrase here is a verb followed by a noun phrase. And then based on this particular language specification or grammar, we would accept sentences or see a sentence like the person has a dog as a valid sentence in this particular language. And a dog has a person is also valid in the language, but something like the dog person would not be valid according to this language. And the way we would discover that is we would try to apply the production rules starting at sentence and doing substitutions, and it would turn out that we would reach a dead end in our attempt to try and apply rules to get to the point where we reach these terminal values, the dog and person. And this is similar to the idea of substitution rules that you would have seen in CS 115 or CS 135 when you were trying to evaluate and understand how racket expressions are interpreted. So this is a very similar process to that. Let's take a look at a different example. Let's imagine that we have a grammar that's going to describe simple arithmetic expressions. So an arithmetic expression could be something like just a number, or it could be something that involves mathematical operators like plus, multiplication, division, and minus, along with brackets. And so we're going to take a look at this particular grammar. Now I want you to note that this is a flawed grammar, and I'll explain why it's flawed in a little bit, but it does have all the features of a context-free grammar. We have our start symbol here, which is an expression. This is what we're trying to identify as our source, as being a valid expression or not. Then we have several options. So this is a production rule that expression is going to can be expanded to be either a factor or a term or a bracketed expression or an integer. So this is just slightly different notation where we use this or bar as an option instead of multiple lines with expression being the left-hand side of the production rule. It's just a little more compact this way. And then a factor can be either an expression plus another expression. So here's where we start to see some recursion involved in these production rules. So an expression can be an expression, a bracketed expression. An expression can be a factor, and a factor refers back to expression. So there's some recursion involved here. It's a very natural thing. And a term is going to be either an expression times another expression or an expression divided by an expression. So this seems like a fairly reasonable way of describing what a valid expression would be. It's a factor or a term or a bracketed expression or just a number. And we have either something that's combined with plus or minus or multiplication or division. So let's take a look at how we take something like this grammar and a particular expression and generate a parse tree. So here's the grammar repeated, and we're going to try and parse the expression 2 plus 3 times 4. So again, we start with our start symbol, which is expression, and now we have some choices to make. There are several ways that we can actually go through and parse our expression and determine whether or not it exists within the rules of the language or not. We expect that this particular expression should be valid. We're going to take a look at this in sort of an ad hoc way, and we're going to be a little more intelligent than the computer would be, or computer program is likely to be, because the computer program is probably going to be going a little bit blind, going through this a little bit blind, not necessarily seeing the big picture of what the whole expression is. Maybe looking ahead a little bit, but not seeing the whole picture. We have the opportunity to see the whole picture here. But essentially the idea of parsing and using these rules is we try a rule out that we think will work. We follow that through to the point of where we either get to the point where we've generated a valid parse tree for the expression, and all of the terminal values from the expression appear in the leaf nodes of our parse tree. Or we get to a point where we get stuck and there's no rule that seems to apply. So what will happen at that point is we would backtrack to the point where we made a choice in the past and make a different choice. And we would continue that process of either going ahead and eventually finding a parse tree that works, or backtracking to a point where we make a choice and making a different choice. And either we get a parse tree out of it, or we exhaust all possible choices along the way. And if we've exhausted all possible choices, then we know that that particular source doesn't exist according to the rules of our grammar. But here we're going to be successful. We know that this is a valid expression, valid mathematical expression. So we should be able to generate the parse tree, and we in fact can. So here we have some choices for how do we expand expression. It could be a factor or a term or a bracket expression or an integer. We're going to recognize we don't have any brackets in here, so again we're going to be a little smart about this. So let's try factor as our first rule, just because it happens to be the first one in the list. And a factor can be expanded as being an expression plus another expression or an expression minus an expression. Well, our expression doesn't have any minus operators in it, but it does have a plus operator. So we can split this particular expression up into this plus being the middle part of this expansion rule, and we want this part of the expression to hopefully be an expression, and we want this part of the expression to hopefully be an expression. So that's our hope. And so at this point we actually will take this plus and put it in as a leaf node in our parse tree, and then we expand two more children, one to the left of the plus, which is an expression, and one to the right of the plus, which is an expression. And now what we have to do is hope that the rest of the expression is going to meet our structure of the language specification. So here we have an expression. Again we have multiple rules, but the only part of our source is just this 2 right here. So we could try a factor, and we would quickly find that that turns out to be a dead end, because we don't have any pluses or minuses in this part of the sub-expression. We could try a term. Again, we would quickly find that's a dead end because there's no multiplication or division operators in this sub-expression here. There's no brackets in that sub-expression, so the only choice really is this int, and 2 is in fact an integer, so we're good. So this part of our original source is now going to meet with the approval of the language specification. So we can continue on, and we can try to expand the expression here. Again, we're now focused on this part of our, this part of our sub-expression, of our original expression, this sub-expression right here. That's the part we're interested in. And again, we could try factor, but that sub-expression doesn't have any pluses or minuses, so that would fail. So we can try term, and when we try term, it turns out that at that point we now have a rule that seems to fit, where we have the multiplication symbol here, and so that's going to work out nicely. And then we try and expand expression to the left of that and expression to the right of that multiplication symbol. And our expression rule here says, well, that could be an integer, so that will take care of this 3. And this expression here, again, we would apply the rule that says it can be an integer, and that takes care of our 4. And now we have a parse tree that is recognizing this as being valid according to the language specification. But not only that, it's giving us some structure as well. So the key to evaluating this parse tree is that we would do a depth first evaluation, which basically means we evaluate the subtrees before we evaluate the root and the larger part of the tree, the upper part of the tree. So in recognizing this particular valid parse tree that recognizes this particular expression, to evaluate this parse tree, once we've got the parse tree in place, we would end up evaluating this part of the parse tree here, where we say 3 times 4 is a term that can be evaluated, and it turns out that that's going to be equal to 12. And then after we've done that evaluation, we can now use that result as an expression value that we can ultimately end up adding to the number 2. So we do this depth first search through the tree and evaluate subtrees before we evaluate their parents, basically. And in this particular case, it looks like things are good, because this would follow the rules of order of operations, which says we should do this 3 times 4 first before we try and apply the addition of 2. And the result of evaluating this particular mathematical expression would be we get 12 out of this subtree, and we add that to 2, and we get a total of 14. And again, the tree is showing us not just the tokens, but also giving us this structure. So far this language looks like it's a good thing. Unfortunately, it's not, because it turns out that we could have taken a different path and generated a completely different parse tree. So again, we would have started with expression, but this time, instead of picking factor, let's say we pick term as the rule that or the non-terminal that we expand to. And this is fine this is going to work out, because we do have a multiplication symbol here, and a term can be an expression followed by a multiplication symbol followed by another expression. So here we have an expression followed by multiplication symbol followed by another expression. That's our expansion in our parse tree, and that's going to be fine as long as this is an expression, that 2 plus 3 is an expression, and as long as the 4 is also an expression. Well, 2 plus 3 is an expression because we can write that as a factor, which is an expression plus an expression. An expression can just be a number like 2, and an expression can be a number like 3. And then we just have this 4 expanded on for the final expression over in this part of the tree. So here we have two different parse trees being generated from the same grammar. This is an example of what's known as an ambiguous grammar, and that's a problem. We really don't want our grammars to be ambiguous. There should only be one way to interpret the source. And in particular, this is actually not going to be a good thing, because if we think about how we would evaluate this particular parse tree, we would end up doing the addition, because we're going to evaluate subtrees before we evaluate the parents, and we end up doing addition of 2 plus 3 before we multiply by 4, and that's going to violate the rules of order of operations. So this particular parse tree is actually not really representing what this mathematical expression should be representing, and so this is a problem. But the bigger problem is that it's ambiguous. That you should never have a grammar that would generate two different parse trees from the same expression. It's really a flaw in the grammar. So here's another example of a context-free grammar that is not ambiguous and handles this problem. So here we have our production rules for expression, term, and factor. But it turns out that once we do this kind of expansion into a parse tree, then we end up, we can follow through all the steps, so I won't do that here, but we end up with all of the terminals are going to be leaf nodes in our tree. We see them all appear here. And also we notice that when we do this evaluation, we're going to end up evaluating this subtree here where we do the multiplication first and then do the addition. So that's going to be good. The question we have to ask ourselves is it possible to do something other than this expansion from the grammar? And the answer is really no. It's not possible. If we try to apply different rules, so really the first rule we applied here was this: an expression is an expression plus a term. We took that, and that became this part of the tree where we have an expression is an expression plus a term. So we have that as our application. The only other reasonable choice would have been, well, we could have a term as our expansion of an expression, and a term could be a term times a factor. So this is maybe okay because we have this multiplication symbol. But then when we take a look at what a term could be, well, a term could just be a term times a factor again, which it's definitely not going to apply to this case. It could be a term divided by a factor. Again, there's no division here, so that's not going to work. Or it could just be a factor. Well, a factor could be a bracketed expression, which it's not in this case, but it could be an integer. So that's actually, now we've taken care of this multiplication, but we would have taken care of, now we're trying to take care of this sub-expression here. Sorry about that. This sub-expression here, and an integer just doesn't cover that. That's not really enough. We need something involving a plus. So that rule is not going to work for us. So we get stuck at that point, and we can go back and we can try and make different choices, but every time we make a different choice, we're going to end up at a dead end. So the only possible expansion of this particular expression into a parse tree is going to be this one and only parse tree, which is going to follow the rules of mathematical order of operations. So a quick summary: parsing is going to depend on a good grammar. Generating a parse tree depends on applying production rules of the grammar. And again, the idea is, one of the basic ideas is to just trial and error. Try a rule, see what it gets you. If it takes you to the point at which you can actually create the parse tree, great. If it doesn't, go back and make a different choice at a point where you had a choice. Production rules themselves could be recursive, and the evaluation of the parse tree is handled by a depth first tree traversal.